We're going to be set. Oh, wow. It wasn't recording before? Oh, wow. That's crazy. Well, okay, it was recording before. All right. Now let's start. We're going to import numpy. Remember, we're keeping the same alias as np. Then import matplotlib, what you just installed, .pyplot as plt. So we're using another alias as well, right? Now let's give it like 2 spaces, and then we'll do np.linspace. So basically, this is giving us like values that are evenly spaced, right? 500. So again, you can use any values in there. So all of these are just arbitrary values. So np.sign, and we need pi times x divided by 10. Let me give you some space. Don't worry if you came late or you're not following, this would be available. Yeah, this will be available. The whole notebook will be available to reference. plc.title, so I want to name what our graph will look like. Particle in a box probability. And then now we want it to show, we want to display. So display. This should give us what we want. Right? So you see between 0 and 10, it's pretty easy. Came here, created the values I wanted to create, the formula for psi. So we're plotting x against psi squared. Give it a title, show it. Very simple, right? So let's say we want to visualize quantum states with block sphere, right? Quantum states with block sphere. In this problem, you need to, let me visualize quantum states with block sphere. We'll need to install Qtip for this. So the same thing, pip install Qtip. So this one, everyone needs to do it. You see, I don't even have Qtip on here, so. Please, if you're following, just kindly indicate in the chat. If you have successfully installed Qtip, could you please indicate in the chat? That would be very helpful. Let me give you the code here. No, I already gave the code before. Yeah. Following. Okay. Have you installed Qtip? If you've installed Qtip, kindly let me know. Have you been able to install Qtip?
Successfully installed, sir. 5.1.
Thank you. Thank you. Appreciate that. Okay. So we want to get the function block from Qtip. So we could say from Qtip imports block, right? Now, this is something called initialization. So here we initialize the, the function, and then let's add some vectors. So we want this to be, in this case, an identity matrix. Let's make it 3 by 3. So we have this b dot add vectors. I'm assuming we're all familiar with what an identity metric means. Zero metric with 0 elements except the diagonals that are 1, right? So if you see all of this, this is 1, right? So be sure. Yep, this is what we have. So let me see who is able to do. It's very easy. This is very easy. Just essentially, we're importing block from Qtip, we're initializing it, and then we're adding the vectors into that block that we just initialized. And this is how we get this visualization. Has anyone been able to replicate it? I'll give like a minute or so because I want us to be able to do quite a few things. The next few is going to be quite lengthy, so it probably would just be best to I will comment in each of the codes as I go. And yeah, has anyone been able to do this yet? I know we have like maybe 20 minutes or so, so let's see how much we can cover. I am not getting anything from anyone. Has anyone been able to do this yet?
I'm working on it, sir.
Oh, okay. Okay.
Almost there.
So just indicate when you're done. So I'll give like 2 minutes.
Okay, sir. Thank you, sir.
Okay, we have 1 minute. Anyone done yet?
I'm having an error I'm trying to rectify.
Okay, what error are you getting? You could share screen. Let's try and debug it.
Okay, sir.
You didn't spell vectors correctly.
Okay.
Where you see that red line on the line, it
Yes, sir.
said that's vectors instead of
Oh,
vectors.
oh.
Run it now, you should be fine. Okay, another thing, in your show, you need the parentheses,
Okay.
bracket, open and close. That's what it's trying to tell you. Run it again.
Oh,
You
great.
should be good now. Fantastic. Congratulations.
Thank you, sir.
Yeah. Anyone else? Okay. Let's do another interesting one. Let's I'm assuming everyone is familiar with quantum physics concepts. Um, oh, that's interesting. Mm, there's a long process in fixing that, and I'm honestly not sure how to tackle that. Usually, I suggest, I need to understand what the problem is. I don't think I do. Do you? I think it's best you just use Jupyter Notebook. Yeah, that would help the best, so that you can keep these visualizations and see, you know, that would be my suggestion. Um, that would be my suggestion. Okay, so I'm going to share my screen again. I want us to do a couple of interesting problems. Okay, so let's do quantum tunneling through a barrier, and we'll plot our graph of transmission coefficient against energy, right? This is going to be quite long, so I envision that it's going to be quite long. So I think you just essentially watch as I go through it, and I will explain, because I don't think we might have enough time. I wanted us to do Schrödinger's equation. I don't know if we'll have enough time, but let's see. Okay, so let's think about the constants that we need. We need h bar, we need mass, we need the energy of the particle, we need barrier height, and we need barrier width. So let's say for the constants, we have h bar. You know what? I need to make sure this is clear. Quantum tunneling through a barrier. All right, so h bar, let's just call it 1. So, h bar is also the same as reduced Planck's constant. So, just for that clarity, so we have, let's say mass is equal to 1.02. Again, all of these are arbitrary values. Like you could, when you have some time, what will help you learn is when you have some time, you take all of these scripts and you redo it on your own, changing values, understanding how each part is interacting. So let's call this V naught. V naught is the barrier height. Let's just call it 1.0. Just for simplicity's sake, let me give this some space so it's easier to read. Yeah. Just let me know if you have any questions, please. Barrier height, and then A, let's just call it 1.0. Let's say barrier width. Okay, so now we need to compute the transmission coefficient. So we need K1, K2, and then big T. I'm assuming like we're all familiar with this concept, so I'm not going to spend too much time. So big T is what we'll call the transmission coefficient. I'm not going to make it super easy, I'm going to create a function and call it transmission coefficient. There are books that I shared with Professor Olayinka that would help you understand how to create functions and why functions are important, so that your codes aren't redundant. Those books, you can leverage them. I believe it has been shared. If you haven't gotten them, kindly reach out to him. It will help you, pick up some of these concepts that are being leveraged here. So here we're finding the square root 2 by m. So 2 times mass times energy divided by h bar divided by reduced Planck's constant. That's our K1. K2 is equal to MP. If there are any errors, please let me know, but I'm basically doing this off the top of my head. Times, so in this case, we have V naught minus E. So this would be all divided by reduced Planck's constant. And remember, we'll have to make sure that E is less than V naught. So the energy is less than the barrier height. Else, so it becomes 2 by this. So it becomes E minus, to make up for that, divided by Planck's constant. Now, based on that, we compute the transmission coefficient as big T. So 1 plus barrier height squared times MP numpy, because we want that sine K2 by A, that's the barrier width, and then all of this will be squared. And then we're going to divide this by 4 times E and we should be good. And then we'll be able to return, because we want, again, remember when we did absolute, see how it's useful here. Do the square of this and we should be good. Now we need to compute the energy range. So as you can tell, this application is a bit more, I won't say complex, but it's a bit more elaborate than what we've been doing. Remember when we use this lane space method to be able to find like a range of values here? So we're using that again. All of this is just essentially an expose of how you can leverage all of these libraries for different quantum physics applications, or other mathematical applications, I should say. So in this case, we say transmission coefficient of E, V naught, and A. We want this to be big E and A for E in E values. Right? So we're given like a range of values that we're going to plot our graph over. So now let's plot our transmission probability. So we're plotting again transmission coefficient against energy. So the probability of tunneling, so of quantum tunneling through a barrier essentially. E values, T values, label. Let's call it tunneling probability. And then what do we want our X label? So our label on the X axis to be, so let's call it energy E. So label on the Y axis, let's call it transmission coefficient T. Then the title, quantum tunneling through a barrier. So we're finishing this here now. Through a barrier. And then let's just say we want a legend here. And then show. Okay. Hi guys, you guys see my first error? Basically hit wrong key. So yep. So that was our values. As energy increases, transmission coefficient increases, tunneling probability increases. So let's say, do we have any questions here? I'm sure there will be questions around the complexity of this code. Don't worry, don't let it bother you. This part is just an expose to show you how you could use Python for a lot more complex or a lot more elaborate use cases. For example, if you could, another one I thought that we could do is the quantum harmonic oscillator wave functions, where we're able to like leverage the quantum harmonic oscillators with eigenvalues and eigenvectors. That's also quite long as well. I don't want anyone to have a not so good Saturday by all of this. So I think in terms of the application, I will stop here. I could do one more with time-independent Schrödinger equation, but that's also going to be quite long. Okay, let me ask everyone. Okay, Mr. Thomas, absolutely. And I would always be available via WhatsApp to answer questions that you might have. Do you want me to do the applications to Schrödinger equation? If you all say yes, I'll do it. If you say it's not needed, I wouldn't do it. It's quite long and I don't want us to drown in details. Mr. George, what do you say? Mr. Emmanuel, what do you say? Mr. Thomas, what do you say? Okay. Oh, yes. All right. Fantastic. So let's do it. Let's do it and let's see what we have. Okay, so we want to do so in this case we're solving for eigenvalues and eigenfunctions of a quantum harmonic oscillator. Okay, so let's see. In this case, hold on, give me a second. Okay, let's see. Okay, so this will be the last one. The eigenvalues and eigenvectors, eigenfunctions. Okay, so let's start by importing our libraries. Oh Lord, what's going on? I'm gonna need to plot. So I'm gonna need to. Now I'm gonna do some scientific computing in terms of some metrics calculations. So especially when we get to the eigenvalue part of things. And I'm gonna need the eigenvalue function. So now we're inculcating some linear algebra. Any questions about linear algebra, I can always visit that outside of this particular, it's a bit, not outside the scope, but we're not exactly touching that. So h bar, which is our Planck's constant, let's call that 1.0. Reduce Planck's constant. So we're setting into 1 just for simplicity. You can, again, put in any value. Just trying to, I'm just throwing our values there now. So let's say this is the length of the domain. So dx, which is equal to, dx is equal to what? Length divided by the number of spatial points. So that would be L over N. Okay. Now let me comment on this to ensure that we have it. So this is reduced Planck's constant. If you have any question, you can stop me, please. Mass of the particle. Everything just, the values are just there for as placeholders. Your job is essentially to take this code, change the values, and see how it behaves. If there are any errors, which can be possible because I'm like typing fast, I'm available to correct them, and I'm also available to give explanations. So now we want to define the spatial grid. Let's call this x, and so 1 negative L over 2, L over 2, and then N. Now we need to define the potential harmonic oscillator. So in this place, like we're constructing it. Let's define makes more sense. potential. If I'm going too fast, let me know. If you don't understand the codes, it is completely fine. But I expect that we understand like the concepts behind it. So I'm gonna go oscillator. Let me just throw this in there. 0.5 times mass times omega squared times x, the spatial grid squared. So that's the equation that we're working with for the potential. So we have omega, again, just for simplicity, v is equal to 0.5 times mass times omega squared times x squared. Now, we're going to calculate the Hamiltonian matrix using finite difference method. I believe we're sort of familiar with that. Finite difference method. I'm just writing all these comments so that when you go through it, it helps you to understand what's going on. And then off diagonal. I'm sure some of us are already getting tired of watching this, but I will be done soon. This is essentially just showing the different applications. I'm gonna be done soon and just quickly go over what we've done so far. So that's diagonal. Now, if you ask where this DAGs is coming from, we imported it from the SciPy library. Diagonal. I need to make sure I'm spelling this well. Off diagonal. So this is actually one of the ways of creating like an identity metric. So np.ones is essentially automatically creating like those principal diagonals with just ones. So taking this here, and then we have 0, -1, 1. I want to convert this to an array. This essentially makes it the metrics that we want it to be. Now you solve the eigenvalue problem. This is a bit longer than what we did before. Eigenvectors. Normalize the eigenfunctions. So I have okay, I need to take my screen up. Eigenvectors. Okay, I need to hurry up. Time is going. Square root and define square root. Then we need to square this to x. Then for psi1, do the same thing. Eigenvectors 1. I'm going to copy all of this because it's pretty much the same thing, just with a little change. Here it changes from 0 to 1. And we start to plot the first two eigenfunctions. So here we're going to give the size of the plot, big size. Could do 8.5. Let's do 10.5. PLT the plot x psi 0, and our label will be okay. So there's a function that we could use here to make it a lot cleaner. Psi 0. That should give, so this would be like the ground state. So let me just put that in parentheses. Ground state. Okay, I'm just going to copy all of this. And here we have psi1. Changes to psi1. So this would be the excited state. So in this case, the first excited state. Am I missing anything? Okay, so now we need to plot the harmonic oscillator V. Let's make this one just to make it clean. Label equal to potential. In this case, we're scaling it. Call this the X label, X, Y label. Let's call it wave function, of course. And then what do we have? Throw in the legend. Here to just show a couple of things I need to add up here. Here to the title. Eigenfunctions of the quantum harmonic oscillator. And then we could just add something here to print the first few energy levels. I'll add this. Values. So, okay, so let's take a look at everything, making sure that I haven't made much mistakes here. So first, we imported the libraries we needed, then the constants. So we have the spatial step, the length of the domain, number of spatial points, mass of the particle. All values here are arbitrary, just for simplicity's sake. Then we had defining the potential harmonic oscillator. So we have omega and the V value. Hamiltonian metrics, we're calculating that using the finite difference method, which I believe we know. If we don't, we can always leverage resources online. Any questions about like syntax and the code can always I can always help out with those. So normalizing the eigenfunctions. I remember we had to do this in undergraduate. So funny. Um, yeah, so let's run this. If we get any errors, we'll fix it as we go. Okay, we're running without no errors. So that's fantastic. You see the ground state, first excited state, and the potential.
Beautiful.
Did we use the Qtip? Oh, Mr. Emmanuel has a code. Qtip packet. Yes, we used it here when we're creating the block sphere. So all of these codes will be available to you. You can play with them. You can change the values. You know, if you don't play with it, you really won't really know what's going on. Some of these syntaxes you have to read up to understand. But even if you understand the syntax, it's important to understand the concepts, like the quantum physics concepts, like what exactly is going on in the back end. What's there is a thought process that is funneling or dictating the codes. You know, we're not just throwing the codes out there. So since this is done, I'm going to go back to the beginning and do a quick recap. We started by looking at like variable definitions, how to equate your variables, um, how to store values in variables. Then we looked at data types, numeric strings, lists, dictionaries. We didn't really touch on tuples, we'll touch on sets as well. Well, remember one of the things that we talked about in math, when you are talking about complex numbers, you use 2i or I to represent complex numbers. In Python, you use J, all right? You use J. Just, oh wait, 1 second. I don't know why things are just popping up on my screen. Oh Lord. Okay, let's settle it down. Now, so we looked at data types and we looked at lists, and we saw that lists are an unordered arrangement of multiple data types within a square bracket. So you could put integers, you could put strings, you could put floats, all within a list. For sets, we saw that it's a collection of unique items. Um, we also looked at how to remove elements from a set, um, how to add elements to a set, union, intersection, those basic set operations. We looked at dictionaries. We saw that a dictionary is an unordered collection of items with data stored in key value pairs. I kind of mentioned that earlier, that think about opening a dictionary and you're looking for a word, and the word that you're looking for is the key. The definition of the word is the value. And we looked at how to, change different values while keeping the key constant. We looked at how to delete a key and a value pair. Today, we looked at like importing packages, so getting packages and using them for your own tasks. Um, we made reference to square roots of a number. We saw that you could do it manually, but we also realized that there are libraries you could use that makes the job easy for you. One thing that is important to know is it's important to figure out like elegant ways of solving problems that aren't super manual, So it's important to understand different libraries, research about libraries, find out how to make use of those libraries. They have documentations that can help you, make use of libraries. So we looked at how to install them, how to call them, how to use them with an alias. We tried for absolute, sine function, cos, and all that. Mr. Jared asked a great question. If you're trying to find pi, how would he do it? So that was a good one. I believe Mr. George also talked about the difference between this 0.499 and 0.5. They're approximately the same thing. Um, there's a whole process going on in the back end about how these numbers are stored in the memory space of the computer. It's different from when we just use calculators, so Mr. Emmanuel raised a great point why sine was giving us negative 0.999a. So we had to make sure everything was converted to radians and all that. Then we went into the application of Python to quantum physics. First thing we did was, simulating quantum states. Well, created a 2x2 matrix and, found the superposition state. If you calculate it by hand, you realize it's the same thing, 1/√2. Then we did the particle in a box solution, where we first did our first visualization using matplotlib. Then we visualized quantum states with Blocksphere. In this case, we did a 3x3 matrix. We did quantum tunneling through a barrier. It became a bit, complex, or I should say not complex, but just elaborate. And then I know we're out of time. We did the quantum harmonic oscillator with eigenvalues and eigenfunctions, and we're able to create this beautiful visualization that we have here. So this essentially ends the expose on leveraging Python for quantum physics. It's not exhaustive of all that you can use Python to do as far as quantum physics is concerned. There's so many use cases that you could use Python for, whether within quantum physics, outside of it. And I'm sincerely happy and appreciative of your participation, joining in for the call. Special thanks to Professor Lainka for having me on. He has been a mentor to me for many years, and I grew up a lot under him in this field and grew up as a man as well under him. So thank you all for having me. Hopefully we'll be seeing each other. I'm available for questions, any support that you might have, any code that you might be writing and you need some help, kind of walking through it. I'm available. I will definitely love to help at no charge. So thank you all.
Okay, welcome, Professor. Thank you very much for the presentation. As a person, I've surely benefited so much from you. I hope that the next time we are meeting, we shall be in good spirits again. God keep you well. To all the colleagues who have been attending, I'm sort of in my place here where I am coming increasingly busy with noise being a Saturday, this a high school, and a lot of students moving up and down. The noise in the background. Colleagues like Jonathan Chuko, Gochuko, I've seen Daniel, I've seen Elvis George. So many of you have been through this lesson which you have attended. Thank you very much. And also thank you, Professor, for giving me this opportunity to host this session. I think you have something to say, Professor. You can air it out before available. Professor, are you there?
Oh yeah, I'm here. Oh no, I have nothing to say. I just want to, I mean, same thing. Thank you all so much. I will be sending the slides to you all.
Okay, thank you very much.
Absolutely.
Okay. We shall meet again, I think.
Absolutely, by God's grace. So
Okay,
take care.
Oh, thanks very much.
All right, bye.